Great, thanks for joining us all. We're going to go through a little bit more detail and then show a lot of demos for Graal. And we just launched GraalVM.org today. Oops, I'm going the wrong way. On the first screen. So go there. We have a lot of code samples. We have documentation, a big new set of documentation, downloads, a bunch of new stuff there. Just launched during the keynote a couple hours ago. So that's something you should check out. As usual in the Oracle talks, don't make any purchasing decisions based on stuff I say, because I'm going to say a bunch of future-looking things that may or may not work before we actually get them out. Okay, so I talked a little bit about this in the keynote, but there are two key aspects I really wanted to talk about. So one is that when we're supporting all these languages, the thing that was very important is that these languages, to be compatible with them, and you want to get to 100% compatibility so your code will just work, they have actually a lot of native libraries in them. So JavaScript has native code in Node. Ruby has a lot of native libraries as well. R has native libraries. Python has native libraries. So other implementations that have tried to re-implement those languages have run into the problem of how do I make those native libraries work. So one thing that we did in Graal is to support native code directly via an LLVM interpreter. So we actually take the back end of LLVM, which generates bitcode, and we interpret that in the same way we interpret JavaScript or Java bytecodes or JavaScript source code or whatever. And so that's a key technology that's in Graal. And I think Chris will have a little bit more to relate to that later. I want to talk a bit about Substrate Vm. So what Substrate Vm is it's kind of the pluggable infrastructure that allows Graal to run in all these different engines. So OpenJDK, for example, likes to control memory allocation and threading, and it wants to control the whole system. And guess what? Databases like to control all those things as well. And so what we're going to do is, with Substrate Vm, you can plug in whichever underlying capabilities you want from the underlying system. So if you want to specify resource management of what kind of memory and what kind of threading you want to use with OpenJDK, you can use the OpenJDK tools to do that. If you're in the database, you can use the database tools to do that. And then in that case, particularly, Substrate Vm provides its own garbage collection. You can also run code with Substrate Vm standalone, where you can compile it ahead of time, which is great if you care about lots of little programs that care about startup and footprint. Rather than firing up a runtime like the JVM, you can just run a binary, and all that stuff's precompiled for you. And then, of course, there's zero cost to interoperate between these languages, and so we'll show you cross-language interop. And one of the tricks that we do underneath the covers to make all of this work is that we actually allow any memory layouts to appear like a native language object, so that if I want a Java object to be native in JavaScript, I don't have to first create a JavaScript object and copy all the data in, or I don't have to create a proxy object that will, for each JavaScript method, then call the Java method. We can actually directly access the data structures, which is a really important thing, and it's a performance improvement as well. And underneath Graal, there's kind of two modes that it operates. There's two levels. There's the kind of a precompiled section, and there is a dynamically computed section. And both Java code and native code in GraalVM can optionally be in either mode. So we can either dynamically compile Java at runtime, or you can ahead of time compile Java. And the same thing with the C or C++ code that you're running from the native libraries. And so one benefit of this is that the Graal languages themselves don't have to be trusted. And so one of the goals that we have to make Graal as secure a platform as possible is to minimize the amount of source code that has access to all the native state and the native heap and free access to pointers. So the Java language itself and Node and all the different languages we support, and there's a lot more language code we have now with all these different languages, does not operate in a trusted mode. So we don't have to trust the JDK. And so then what that means is the host language level, which is where the trusted code runs, it's still managed and garbage collected and bounds checked. So even that C, C++ code, we can garbage collect that if necessary. We can also, even if the Java code is running precompiled, we'll still have all those features. And then we create a whitelist and only expose certain parts of that code to the dynamic languages. And the dynamic languages then can also be put into a memory box or a time box to make it a little bit more safe to run untrusted code. One of the big applications for Graal and this architecture is where you have like a large Java application. You want to allow people to upload some code to customize it. So for example, NetSuite is using Graal now to provide SuiteScript, which is JavaScript extensibility, and they use the memory boxing and time boxing, but it can access all the native Java data structures underneath. And of course, all that stuff you can get to with no boundary crossing costs. And so the overall goal here is that your code can run on the Graal ecosystem, and you're going to get its availability from all the different languages rather than just being available in the language it was written in. And you're going to get that code to be available in all these different embeddings. So it's not just in, if you wrote the code for the JVM, it's not just available there. It's also available in the databases and in Spark, Nginx, or anything else where it may not otherwise be compatible. And then you can use the common Graal tools and infrastructure and all the optimizations across all that code. So it's creating more multiplicative value add. And I mentioned before that one of the key technologies in Graal is that we can make any memory layout look like a language object. And it's that logical physical data isolation. So one example research project that we did, actually Daniela did, who's sitting here in the front row, allows you to have access directly to the network buffers, so you didn't have to create new JavaScript objects every time a row or a column came back from the database. You could just point to those network buffers. And so you can see a pretty high speed up. This is just a research project yet, but that's something we're working on doing in the product. And I want to talk a little bit about the roadmap, and then we'll get into demos. This is Oracle code. So this is mostly about looking at code, so I'm not going to do too many slides. Chris will get into the demos in a second. One feature we just released now today is called isolates. So this is something that you've had in browsers, but hasn't been available in the JVM, where you can create multiple heaps that are provably separate, and they have isolated objects that can't reference each other, and they're garbage collected separately. And so if you want to have separate tenants and kind of manage them separately, create a heap, have a sub-application, allocate things in that heap, then throw it away separately, you can do that now with Java, with isolates and Graal, and that works in all of our languages. We do have research. One of the things, of course, we aren't supporting now is Java or PL SQL as truffle languages. So there is a little bit more cost there, and they don't participate in our tooling infrastructure, so we have some research projects to add those. Obviously, if you're running Graal on Hotspot, there's not an issue with that. But if you're running Graal in the database, you're not using the Graal implementations there for those languages. I mentioned the database driver, but there's a set of other Graal-enabled libraries. We did a paper a little while ago on smart collections that can get more optimization out of collections by using some of the Graal features in the library. There's some security features we're working on, such as running the C code in the LLVM interpreter in a managed sandbox, also doing dynamic taint tracking for looking for untrusted input that's getting put into like a SQL driver and trying to look at SQL injection attacks. Today we have Linux and Mac OS available for download, but we are working on support for Windows as far as operating systems goes. Today most of our optimizations have been focused on x86. But we also have a backend actually that Red Hat contributed for ARM, and we're now putting some people in from Oracle to make that port better. There's actually a lot of people that are caring about the ARM ecosystem, and I guess Apple announced that they're going to move to ARM soon. So we're going to really try to ramp up the support for that processor. And then also recently, Java 10 is now having Graal as the experimental compiler, so that I guess if we pass the right command line flags, you'll get Graal available, and you can do some things with that. That's just the compiler. It's not the rest of the languages or Substrate Vm. But there is some work to incorporate Graal with Substrate Vm as well into JDK. And then our version, if you download it, you're getting JDK 8. Most of the customers we talk to are still interested in staying on JDK 8. And so that's where we add features. So we're going to be trailing a little bit on the Java side, and the Java guys are going to be trailing us in terms of adding our features. But so there's kind of like that. Everyone wants to wait until the other guy's stable thing. So that's kind of the infrastructure we have. So I'll take any questions now on this stuff, and then we'll go into some code demos. So. So one of the things I talk about, VMware is designed to interact with your software at the operating system level, right? And so the only knowledge it has of what your program is doing is whenever your program makes calls out to the OS. We're actually executing every instruction of your program, and so we can watch what your program is doing. So you can ask like GraalVM. One of the things we're looking at is that program mining Bitcoin or not? Like, it turns out that we have problems with people like running Bitcoin, miners, like and hiding it in open source packages, right? So let's say I want to detect that. Well, we can actually detect that because we have access to the internals of what your language is doing. And so that's one major difference, right? So we're compiling the code. VMware, you have to provide the code that's compiled. It's a different level of virtualization. Any other questions? Comments? All right, let's go do some code.
Just swap the display.
Swap
over.
this, yeah.
So I'm Chris Seaton. I work on one part of the GraalVM project, but I'm going to show demos from all parts of it. GraalVM is a really large, ranging project. No matter what sort of software development or operations you work in, there's probably some part of GraalVM that's of interest to you and is applicable to what you're doing. The place to get GraalVM, the first step, is to go to graalvm.org. There's a website there which has lots and lots of documentation and has the actual download links to go and get what we're looking at. I've already got the tarball which I've downloaded and extracted and set up. So I won't show you the setup process in detail. I'll get straight into the demos. Let's make that nice and large for you. Okay, so what is GraalVM? You may be thinking some of these concepts are a bit abstract at the moment. So one thing GraalVM is a JVM. It's a superset of the JVM. It provides more than a JVM but it provides the same as a JVM does. But it runs your Java code faster than a standard JVM would. So I've got a Java application here. It's called Top 10. And what it does is it takes a set of files on the command line and it tells you the top 10 words it finds in all those files. And it does it using the Stream API. It's a fairly small, simple program. But you can imagine we run this with perhaps a large input, so we'd want to run it as efficiently as possible. So GraalVM does include standard... GraalVM does include standard commands like the Java-C compiler and the Java command. So we can compile that top 10 application using the Java compiler. And then we can run it using the Java command. And I'll use the time command to time how long this runs. Now I'm using the time command because I want to run this, I want to time how long the entire thing takes. So I'm not running a micro benchmark, I'm running the complete application with a large input from beginning to end. I'm asking it how long is that going to take. When you run Java from the GraalVM, it's configured to use Graal by default. So I'm using Graal already here. This takes about 17 seconds. And we can disable Graal by using this command here. I'll say I want to disable using the JVM-CI compiler. JVM-CI is the API that Graal uses. So I say I want to disable that API, and I'll run the same command. So now it's using the standard hotspots server compiler, also known as C2 or Opto, to run that same program. And it's going to take it a little bit longer to run that.
Gosh, Chris, if the Graal program took 17 seconds, or 20 seconds looks like there, how long are you going to wait during this talk for this? Okay.
So it takes 21 seconds. So this is a drop-in replacement for Java that's running a program in 17 seconds instead of 21 seconds. And in an environment where we're used to getting 1% increase in performance from the JVM is pretty impressive, this is very impressive. And this is why Twitter are deploying Graal themselves in production at the moment, because we get this real impact on performance, which translates to real money in terms of running a large data center. But that's running a large input. If we run Java on a small input, it's not quite so impressive. This file is pretty small. It's only a few hundred K, but Java still takes quite a long time, really, to start up and run that program. This has been historically something Java isn't the best at. If you write something like a command line utility, it always takes a little bit of time to start up. And that's because the JVM is quite a complicated, sophisticated thing. If we want to run small commands, we can use something in the JVM, in GraalVM, called native command. So what I'm going to do is I'm going to run native image on the same top 10 application. What it's going to do here is it's going to compile that Java application down to a single statically linked binary that doesn't run on the JVM. It's a native application. You may be thinking what it's doing is it's taking a JVM and sticking the jar inside it, It's not doing that. You may be thinking it's creating a native application which links to lib.jvm. It's not doing that. It's creating literally a single statically linked executable which implements this Java program. We can run the O tool on it to see what it links to. So it just links to the system libraries there. It doesn't really link to anything. And if we look at the size of it, it's only 5 megabytes or so. And if we run this now, I'll run the last one again. So it takes 0.385 seconds. If we run the native one, it runs much faster. So what we've done here is this is an option for running Java commands without that kind of startup overhead. And it also means you don't need a JVM to run this. So I could take this 5 megabyte executable, and I can install it on a system which has never had the JVM installed, and that's the entire Java program. The way it works is it examines all the code that you're actually using in your application. It walks through all the classes you're using, and it compiles in parts of the JVM you need, such as the garbage collector, and it boils it all down to this single executable. So if you're interested in high-performance Java, we've shown it can do that. If you're interested in fast startup, low-footprint Java, we've shown it can do that as well. So that's Java, but we talked about other languages and polyglot. So what I have here is an application which is written in JavaScript inside the Node.js framework. So it loads the Express web server. And what I have here is I say I want to use a bit of Ruby code here. So I use this API polyglot eval. I say I want to execute some Ruby code, and then Ruby code is inside this string here. So I'm requiring a Ruby library. So say there's some Ruby library I've got that I want to use from JavaScript. It's called the color library for working with different colors. And I simply want to return this module, color RGB. Then I can use this within my Node.js application. I have an endpoint here. And what it's going to do is it's going to take the name of the color, and it will look it up in that color module by name, and it will return it as an HTML color, so a hex encoded with a hash in front of it. And notice what we're doing here is I haven't had to do much ceremony to do this interop. What I've returned is a Ruby module, and then I'm calling methods on that Ruby module, which are returning objects, and I'm calling Ruby methods on those objects. I haven't had to wrap the object, haven't had to say create a proxy for anything. I simply naturally say I want to call these methods on this Ruby object. I won't run the module install commands because I don't want to be dependent on the Wi-Fi, but we can simply install using, again, GraalVM, a Ruby module. We can install, again, using the GraalVM version of these commands, Express. And then I can run the server. I say I want to run Node, and I say I want to load all the polyglot libraries, and I want to run on the JVM in this case. And then I can go to that endpoint, so it was CSS and the name of a color, so I go to CSS aquamarine, and it will tell me what the HTML value of that color is. So the JavaScript is running the server, and then the library is written in Ruby. The idea is if you have a library which is already written in another language, you can take that from that ecosystem. You don't have to wrap it to create a version of that library. You can simply naturally use it from one language to another. And this same demonstration here would work with a Python library, or an R library, or a Java library. If people write other languages in the future, it'll automatically work with those. All they need to do is change that language identifier there. Let's try a more sophisticated example with a library that you really might want to use from Node.js because it's not actually available. So I've got an application here that is, again, it's running in Node.js as the outer layer. I'm going to use some Java here. So JavaScript doesn't have great support for big integers. There are libraries you can get, but they have to work in quite slow ways to work around Java's numeric types. So I'm going to say I want to use from Java the type Java math big integer. I'm going to write an endpoint, and what I'm going to do is I'm going to create a big integer, 10, I'm going to raise it to the power of 100, I'm going to add 43 to it and convert it to a string. And then I'm going to use R, and I'm going to draw an SVG image of some shape of some points moving around. So we're using Java, and we're using R, and we're using it from the Node.js as the outer language. This one takes a little longer to start up because it pulls in an R module dynamically. But if I open up the browser, so it loads an R package there. So what we have is, that's that big integer printed out as a string, and then we get this SVG image printed in line. So this is a use case you can imagine is very practical, something you might genuinely want to do. If you have a JavaScript Node.js application, There are lots of JavaScript graphing libraries, but they're not always terribly sophisticated. The R ones are very sophisticated, have lots of clever stats libraries you can use. And it wasn't hard to write that simple application that combined R and Java, and it uses each language for what it's best at. So you don't have to worry about what language your ecosystem has. You can pick the best tool for the job. Another aspect of GraalVM is operations and tooling. The idea is because all these languages work in a similar way, they all work on top of truffle. So truffle is the layer that the languages all talk to. And the idea is all we have to do is implement tools once for truffle, and then all those different languages can work with the same tools. So you get that one point where you can implement something once and then use it from all these different languages, including languages you may not know about, someone else is using. And if you have a program written in more than one language, the tools work across those languages. So I've got a JavaScript application here, a FizzBuzz application. So it simply goes from 1 to 20 and it prints out FizzBuzz based on the classic programming problem. The reason I've chosen this is because it's got different branches which are taken at different points in the application. So I'm going to run the GraalVM version of JavaScript, and it printed out there. Notice how nice and fast that started. But I'd like to debug this. I'd like to see when we get to FizzBuzz. So what I'm going to do is I'm going to run the JavaScript command, and I'm going to give it this extra flag now, inspect, and that's available for all these languages. It comes from the GraalVM system. So what it does is when I run that is I get a URL which I can open in Chrome. So Chrome has a JavaScript debugger built in for debugging JavaScript applications. I think you can use it with Nodejs as well. And what we've done, I don't know if I can make that large, there you go. What we've done is we've written a layer which can interface with that. So what we've done is we've started the application and it's paused on the first line that does some actual logic rather than just a function declaration. So I can set a breakpoint on the line I'm interested in, and I can continue execution until we get to that point. And then you see we get features here such as it prints out the current value of n, and it prints out a call stack that I can navigate through as well. We have things like watch points, and you can inspect other variables. So I think if I go to the program, I can print out, I can see the value of n. Nope, sorry, not sure how to do that. But there we are, we've broken on this point in FizzBuzz, and then I can remove the breakpoint and I continue executing, and it finishes. But Chrome Tools already does debugging for JavaScript. It does it for the built-in version of JavaScript it has. We can use it for other languages to do exactly the same thing. So I've written another version of that FizzBuzz program, this time in Python. I'm going to run the Graal version of Python. And I get exactly the same thing. I get a URL, which I can open in Chrome. And I get a similar interface. So again, I can set a breakpoint on the line I'm interested in, and I continue execution. And again, I get that debugger, exactly the same interface, exactly the same utilities where it's telling me the current value of n. And this isn't something that's built into Chrome. Support for Python, you don't normally get to see this, but our backend can work with all these languages. So I'll continue execution. And again, we can debug Ruby if we want to. Set a breakpoint I'm interested in and run. And again, it tells me we've got the value of n at that particular point. And for R again, we can debug. A lot of these languages don't always have good debuggers of their own. If someone's written a fairly small language that doesn't have much support from industry, you may find there's not many particularly good tools for it. If you write your language on top of the truffle ecosystem, you get all these tools of the same quality as you do for the main languages like JavaScript. And again, we can set a breakpoint in R, and we can run it around. Remove the breakpoint. Again, it tells us the value of n using the R way of talking about things, and we can continue. That's just one tool, the Chrome debugger. We also have tools for things like profiling, and there's an API to build your own tools. So you can write one tool and have it work across all these languages, in the same way you can write a new language and get all the tools existing. So it's a real sort of force multiplier. You have this one point where everything can come together and everything can go in and talk to each other through it. And if you have a polyglot program, you get polyglot debugging. One tool we have that we've modified to work particularly well with Truffle is JVM. So I'll open JVM, which is the tool that you get inside the JVM normally, but we have a modified version of it. I'm not sure I can zoom that, but I've got screenshots I can show you when we come to it. So I'm going to run the Java top 10 program again with a large input. And I can open that from Visual VM. And I can do things like I can take a heap dump. I'll stop it then, and I'll show you the screenshot then. So we can see our Java application tells us the things like how many objects it has inside it. And these are really good tools for Java, and Java can do this because it can introspect itself. And this is one of the reasons why a lot of people program on the Java platform, because you get this sort of high-quality tooling. And JVM and the GraalVM extends this to work with other languages. So if I've written a Ruby application here which renders a template in a loop. I've done that so it generates quite a lot of objects and interesting garbage and things like that. And I'm going to run Ruby for that application. I'm going to say I want to run on the JVM because the JVM has better introspection facilities than the Substrate VM does. The Substrate VM trades off that introspection for being able to start much more quickly. So now I see a Ruby application there. It has a picture of a cup, which is the Graal logo, and I can perform a heap dump. And I can see how the garbage collector is working. So if you ran an existing implementation of Ruby on the JVM, such as JRuby, you'd see Java objects here, and this is what we see by default. And that's a real limitation in that the languages are never like first-class citizens. You always see like the Java version of things, and it's always in this sort of twilight zone of not really a separate language. But what we can do is I can say, instead of the Java heap, I want to see the Ruby heap. And it will translate it into Ruby objects for me. I'll show you the screenshot again because it's larger. So now we see that I've got string objects and symbol objects and class objects, array objects. It tells me which objects are large, and it's lots of hashes that tend to be large in this case. And it tells me how many of those objects we have. I can do things like I can see what are all these symbols. So I can double click on them and I can see these symbols are all these different names of encodings and things like that, and types and whatever is going on inside this Ruby application. And again, if you write an adapter for JVM which explains how your language likes to be able to look at objects, what those objects mean in terms of your language, then you can run that application. Okay, let's go to a more extreme sort of polyglot. People running languages like Python and JRuby on the JVM already. I've said why they aren't quite as sophisticated as what we do, but let's take it to another level. What I want to do is run a C application on the JVM. What I've got here is a version of gzip, so the GNU zip compression utility. I've got a version that's just one single file. So CSAIL have this project where they have single file versions of applications for doing research on. It's just much easier to work with. What I'm going to do is I'm going to compile that application using the standard version of Clang. So it's not a special GraalVM version of Clang, it's my system Clang. So I've compiled it, that gzip, but I've got it to emit LLVM bit code rather than emitting machine code. So if I look at what files I've got the original C source code, then I've got this bit code. So that's a machine-readable version of the program as LLVM intermediate representation. What I'll do is I've got this small file, and that's what it looks like. It's from Great Expectations. And what I do is I'm going to compress that using the system version of gzip. And what I do now is I'm going to run our LLVM interpreter on the gzip bitcode. So I'm saying I want to run this bitcode file, and I want to decompress that file I just created. Runs nice and quickly, and then I can cat the file again, and it's been decompressed. So what we're doing there is we're running a C program on top of the JVM. It still uses native memory. We have projects to run this on managed memory instead of native memory, and to provide safety. In this case, it's running in native mode. You can run C applications like this, but one of the main reasons we've done it, as Eric described, was in order to be able to run C extensions for existing languages. And like all the other versions of GraalVM languages, this provides a sort of level of abstraction. And that when you have a C structure and you read fields from it, that could be a real C structure, or it could actually be a Ruby object, or a JavaScript object, or an R object. And you can think you're reading from memory, but actually it's being redirected into doing something else. And that provides a level of abstraction that allows you to do things such as read from memory that's actually being done via a remote procedure call or something like that. Okay, so that's about running things within the JVM and running things using Java libraries. Perhaps what we'd like to do instead is take libraries from the Java ecosystem and use them within other larger native projects. I've got a library here that's from Apache. It's the SIS library. It's for doing geo information, so be able to do coordinates on globes and things like that. It's a real off-the-shelf application. I've got this application I've written here which uses it. It takes 4 doubles and it tells you the distance between them is a lat long using the library. So different utilities have assigned distance. So again, I'm going to compile that. And I'm going to run it. And I'm going to give it the coordinates of London and New York, and it tells me they're 5,500 kilometers apart. What I'm going to do now is I'm going to compile that. Like we did before with the top 10 application, I'll compile that to a native application instead. So again, this produces a single standalone statically linked binary. It doesn't need a JVM to run. I can run that to produce the same result. And notice how much faster it started because of it's natively compiled now. But what we can do more interesting here is we can add this C code to it. I'm going to say that I want to add a C entry point called distance, and it's got those 4 doubles, then it runs the same code. And then if I compile this saying that I want a shared library instead of an executable, what it's going to do is now it's going to produce a dynamic library, so a dylib on macOS or an SO on Linux. And again, this doesn't have any dependency on the JVM. It's simply native code, and you wouldn't know it's any different to as if you'd written the whole thing in C, but you've produced it from this off-the-shelf unmodified Java application. And now I can write a C application to use that. So it automatically produces a header for you, libdistance.h. That's automatically generated with the same signature. I set up a few things. So I create an isolate. I create a thread. This gives you the option to do things such as have multiple versions of the library and the Substrate VM running at the same time, kept separate. And it passes from the command line and it runs that code. So I can compile this driver application using my standard version of Clang. And I say I want to link to that lib distance, and I can run that application again to produce that. So this means now that if you have a Java library which does the functionality you want, but you have a native application, or you have an application written in some other language which has an FFI, like Lua or something like that, you can now use Java libraries from the Java ecosystem in that application. And when we talked about running Graal in the database, this is effectively what the database does. It links this library, and then the database loads it. And the Substrate VM is designed to be well behaved enough that you can put it in as a dynamic library. It doesn't try to own the entire world like the JVM does normally. We've packaged that up into a utility called Polygon Lib that provides an interface to be able to use that automatically. So this is an API which you get in GraalVM by default that includes a function, basically polyglot context eval, that allows you to run any language that you want from the Graal ecosystem in a native application. So you know languages like, implementations like V8 have an API that you can use to embed and use them, and that's what Nodejs does. This is the same thing, but for all the languages you get in the GraalVM. So what I do is I eval a string that I get on the command line, and I print it out, basically. So eval and print it out. And again, it's simply using the system version of Clang to compile that. And if I look at what that depends on, you can see it depends on this lib polyglot, which is provided by default in Graal. And then I can run that. So by default, it evaluates stuff as JavaScript. I can explicitly say run it as JavaScript. And I can use a language like Python as well. So if you have a system which has some sort of embedded scripting language perhaps, or uses JavaScript as an embedded language, and you can now replace it with this API instead, and you can run any language then. The interface I've shown is just eval, but it includes sophisticated things such as being able to call methods, index arrays, things like that. And finally, Polyglot in the database. So this is an application of all the things we've shown so far, just one application. You can download this multilingual edition of the database from this link. Multilingual being like polyglot. I've set up already because it takes a bit of time to set it all up. But basically, I have the database running in Docker, and then I have Docker running here. So all I want to do is, that's all the setup commands. I'd like to be able to use JavaScript libraries from the Oracle database. So there's a huge ecosystem there. For example, there's good libraries for doing things such as validating inputs, because people do that a lot in JavaScript. If I go to the NPM website and I say I want to validate things, so I'll search for validator. There's this library here that does string validation, can tell you if things are valid email addresses, things like that. So there's an example here, validator.isEmail. Tells you if something's a valid email or not. So I'd like to be able to use that from within the database. If I'm using it on my client, I'd like to be able to run exactly the same code in the database, so I don't have to program it twice, and I don't get it wrong when I translate it, so it's doing something slightly different. And what we're going to do is I'm going to install that validator library, and then it has a sort of sub-package of plugins. And then we can use this as a command, db.js deploy. And what I'm saying is I want to deploy that node module into the database. And then we can load up the SQL query interface. And what I'm going to say is I want to select validator is email and see if this email address is a valid email address. And it tells me 1, meaning yes. And if I run something which doesn't look like an email address, then it tells me no. So I can have this in my stored queries, I can have this as part of my normal queries, and this code is being dynamically compiled if needs be, if it's on a hot loop, and being inserted into the database. And that doesn't just work with JavaScript. It's multi-language edition. It's not just JavaScript edition. So if you have other languages you want to run, you can insert it into the database as well. So where can you get more information on this? There's absolutely tons of information if you go to graalvm.org. You can download the system from here, and you can recreate those demos that I've showed you there today. There's a community edition, which is all open source, free for production use. You can take that, you can build it yourself, you can use it in production if you want to. There's an enterprise edition, which is free for evaluation, and you can talk to us if you want to talk about commercial use or support. Yes, there are some components which are in the enterprise edition, but not the open source one at the moment. And the enterprise edition is available for macOS, whereas the community edition isn't available for macOS at the moment. But you can evaluate it, of course, so you can see the impact of the difference if you're interested in that. GraalVM, as I say, it's a really large, wide-ranging project. There's a very large group of people working on it. This is a tiny proportion of the people working on it now. This was a few years ago. That's a list of the people who have been involved with the project at some point. This shows you how much Oracle is investing in this and how important we think it is to create this one platform where everything can go through. And we think it'll be a real force multiplier for being able to use different languages, different libraries from different ecosystems, and enable you to program as you want to. So if you want to use a library, you can use it. You're not restricted because you made some old choice to use one particular platform. We have a Gitter room where if you want to come and talk to us and see about anything that we've talked about today, you can go to this Gitter room, or you can tweet me. If you want to tweet me while I'm still here today, then you can. You can come and talk to me and see on these demos again, or I'll talk you through how they work. Thanks so much. Eric, do you want to conclude?
No, I guess that's it. I mean, graalvm.org. Check it out. We launched it there today. So, and then any questions from anybody today?
How does it work in the server and
Go ahead.
how does it work in the server and
Well, so he showed you how the native library works, right? So basically what we did is we took the native build and we used that to run the infrastructure, and then you can also dynamically run classes. So when he's dynamically loading the JavaScript package, then that's being dynamically compiled. That's that top level piece. We have a question over here.
I think you mentioned that Twitter uses Chrome.
Yes.
That it's 11% faster. How can it be faster if there's a layer on
So what's faster is that the compiler is a lot more aggressive at identifying object inlining, and Graal itself was actually a compiler written in Java. So the way Graal works is it first compiles itself. So it allows us to write a compiler itself in a higher level manner. So like the compiler that's been in Hotspot for the last 15 years or so is called C2, and that's written in C++. And so it's written kind of in a low level that kind of knows it's a compiler. Like here's the left operand node, the right operand node. You aren't just saying A plus B. You kind of you're operating at this lower level. So Graal has some infrastructure called snippets. It makes it much easier to write compiler optimizations. And so the compiler itself is just a better compiler. And so languages with more abstraction, like the more abstractions you use, one of the things Chris didn't show today is we have a stream API. So like it runs a lot faster. Or actually, you did show
the Java application.
Yeah, I mean, so the stream application, like the Java 8 stream API, this stuff here, this is actually pretty abstracted, and so we can do like very substantial speedups on this depending on the size of your program. Which how much of speedup you were showing in the example that you did? It was like.
It was 23 down to 17 or so.
So like that's what 30% faster, right? And so like the more abstractions they have, so if you use like Stream API in Java 8, or if you're using Scala or things like that with more abstractions, we have more like gunk we can get rid of, and so you can see more performance improvement there. And at the end of the day, Graal, let me have the projector back. Graal is still generating snippets of machine code. So we're running the same kind of thing that Hotspot is. And so when you're running Graal in Hotspot, you're still running the Hotspot runtime. Why is this not? No.
Specifically, the optimizations that Graal includes that Hotspot doesn't are things like partial escape analysis, which allows you to remove all location of objects even if they're on some paths they escape. And the reason that's in Graal but not Hotspot is because it's so much easier to work in Graal because it's simply a Java application. People think about JITs as being really, really complicated applications, like system-level applications, but really they're not. They're a function from bytecode to machine code. And machine code is just an array of bytes. So there's no reason why we can't write that in Java. And when we do, it's much more easy to make these changes, and we have done because it's easier, so we get better performance.
So yeah, so what's happening here is when Graal sees code that's going through the Truffle API, we're compiling code, and they're just little chunks of code. Because what the VM is doing is it's running interpreters for the stuff that doesn't see a lot, and the stuff that's in a hot loop. Then the hot loop stuff gets the. Is this going to work? The hot loops here kind of get compiled code snippets in it, and it can do compilations in the middle of a loop. So if it sees, okay, I've gone through this loop enough times now, I'm going to actually replace the interpreted logic with the compiled logic, and then you're running just kind of native assembly code like it was compiled with a C compiler. But it's actually even more optimized because we have the profile of what the program's actually doing. So we actually have some examples where you can show JavaScript running faster than C, and what's happening there is the profile has actually allowed us to do a more application-specific compilation where we can say, oh, hey, the data types are looking this shape. So we can actually compile for that particular data type as the assumption. Hey, most of the numbers in this column are not long numbers. They all fit in a 2-byte integer or a 4-byte integer. So we'll compile and use smaller size integers and then throw an exception if we get a big one. And if we see from the profile that, hey, this column always has like money in it, we can just multiply by 100 and count pennies. We can use integers rather than floating point or big decimal or whatever. Those kind of optimizations we can do. Does that help?
Part of the reason why it's so much work, though, is because it's so difficult to do within Hotspot, within the C2 compiler. The theory work is complicated, yes, but implementing anything in Hotspot is very, very difficult these days. There's very few people who can do it. When you look at the source code of Graal, I'll take you through some of the source code of Graal if you like later and show you how high level it is and how easy to work with. So we have PhD students who come and add really significant optimizations to Graal without much effort.
So. Don't listen to us, right? I mean, listen to the Twitter guys, right? They're actually found that they, if they're running 10,000 servers and you can save 10%, that's 1,000 servers you don't have to buy, right?
I'm just thinking maybe an awful lot of their stuff
They wrote it. It's running in the JVM today.
It's in Scala.
It's in Scala.
So it does tend to generate more garbage and things like that.
Yeah, the more abstractions you do, the more performance you get, right? I mean, if you're running code that just kind of looks like it was C code ported to Java, it's probably not going to see a big impact, right? Okay, so start from left to right. Go ahead.
So one of the features that caught my eye was you were saying you could produce standalone static binaries, right? So you could take a Python program and turn that into a static binary.
No, this is a really common misconception. We can take a Java application and turn it into a statically linked binary. We can take a Python interpreter written in Java and turn it into a static binary. We can't do the next level and turn the Python program into a static binary.
So if you notice here, the only thing is that you can precompile are Java and native code. And the reason for that is we need static types to do native compilation right now. Okay. So Java is kind of this neat language that it has static typing, but it's dynamically compiled. Other languages you support, and we've really focused on, are dynamic languages that are dynamically typed. And of course, C is something you can do either way as well.
Something you can do, though, is the way the Substrate Vm compiler works is it runs your Java application up to a certain point and then freezes the heap and compiles it into the binary. So what you can do is you can run Python or Ruby code during compilation. So you can do things like initialize your libraries, create objects, create classes, stuff like that. And then when you start running the compile code, they just magically appear in your heap.
So it helps with it's a startup thing. Okay.
So looks like GraalVM is great, much more better than Hotspot VM in performance and also interoperability. So why should I use Hotspot at GraalVM?
Well, so Hotspot, remember, it's a VM, right? So like when we're running in Hotspot, we haven't, when you're running in OpenJDK, you're running with the OpenJDK garbage collector, for example, and JDK has very good garbage collection, right? It's actually much better than the garbage collector in V8, for example, right? JavaScript, VMs are not really designed to run a lot of garbage because you're running short-running web pages. They care more about startup. The JDK is really designed for servers, and so if you have like big heaps, like gigabytes of heaps, and long-running applications, Hotspot I think has like by far the best server class garbage collection, and so you want to use that. Like in the context of the database, Substrate VM has our own little built-in. It's a much simpler garbage collector. But usually what's happening is you're doing one select statement, and at the end of that select statement, we throw away the heap, right? So we don't actually need to collect garbage. We just throw away heaps. And that's the way databases have always been built. So you don't actually keep around language state past the one JDBC call when you run with Substrate VM in the database. And so we have a simpler garbage collector. Node has a simpler garbage collector. Hotspot has a great garbage collector. And there's a lot of contributions from the community into garbage collection.
If I write my code only in Java versus different Hotspot,
if you're running short-running code, then GraalVM is going to make a lot of sense, right? It's going to make more sense probably. If you're running long-running code that's going to be in a server, run it in Hotspot, but with the Graal compiler in Hotspot, right? So Graal runs in Hotspot, right? So we aren't necessarily, like Graal and Java are not always the same thing, right? So we can mix and match the components of whichever infrastructure you want. So hey, let's say when you're running Graal in Java, what we add is multilingualism to Java that's much more effective, right? We add the compiler is faster, right? But you're still getting JavaScript garbage collection. You're still getting the JVM's garbage collection. You're still getting the JVM's implementation of all the JDK, right? You can compile GraalVM and run Hotspot.
It gives you another degree of freedom. In the same way, we're now letting you choose which language you want and which libraries you want from different languages. We're now also letting you choose, do you want high startup time, do you want quick startup time and low footprint, or do you want best peak performance? And you can choose between the two depending on which situation is appropriate for you. So we're giving you all these extra degrees of freedom.
We still haven't yet supported people running Java and V8 as the VM.
No.
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 But we actually have a little research project to run Graal and Chrome so that you can have, we'll call it GraalVM, where you can like run R or Ruby instead of JavaScript. But that's just kind of a little fun little research projects going on. We had more questions over here.
I wasn't quite sure how the Chrome debugger was working. So that was instrument against the Truffle?
The Truffle has a standard way of writing, a standard way of applying a debugger on top of your language, and then it simply interfaces with Chrome via a published API they have. So it opens a socket, talks to Chrome, and it simply tells them that you're on this line of this file, and Chrome prints that, and you tell it this location is a variable and it's got this value, and Chrome prints that. So Chrome doesn't need to know about the language, it simply gets told. Yeah, yeah.
Right.
Yeah, because if it does support other languages like CoffeeScript, I think, and it uses source maps to do that.
Most debuggers now have a remote access protocol and are multilingual.
You can do the same thing with NetBeans. The same demo I showed you works with NetBeans, I think.
Just a different protocol, right?
Yeah.
Yeah, that's kind of that's the JVM-TI, I think it is, the Java's kind of API for, and then we support the JavaScript API.
And again, it's another one of those linchpins where everything can go through and you can swap out the back end and everyone can work the same, just with a different back end.
Any more questions? I think we're probably well out of time at this point. Not that far, only 5 minutes late. All right, well, thanks everyone for your time. And we're available for more questions afterward.